So in the previous part we have discussed about the change of state. Okay. And now we will discuss the last part of calorimetry, that is latent heat. Okay. What is it? Whenever we are talking about change of state, all the time we have mentioned one thing, that the temperature remain constant, and it is happened when the solid converts into liquid due to the application of heat energy, or liquid converts into gas. In every case, we have told that at the time of state changing, the heat energy, the temperature should be constant. But that time, we have given heat energy to the body. So where the heat energy goes, basically? Similar thing, whenever we have extracting heat energy also, that means when liquid converts into solid, that time also the temperature remain constant. The temperature remain constant and we are extracting heat energy. So it seems to be that we are giving heat energy or extracting heat energy from a body, but temperature is not changed. Where this temperature goes? This temperature, where this heat energy goes, this heat energy is responsible for changing the state, and that heat energy is known as latent heat. So we can say at constant temperature, the heat energy absorbed or liberated to change the state is known as latent heat. That heat energy which is not increasing or decreasing the temperature, it is used only for changing the state, that is known as latent heat. Now the question has come, if the temperature is not increased or decreased, then where this heat energy goes? I am telling you one thing, from a very childhood age, that from class 6 onwards, you know that the molecules in a solid, they are very much closely packed. You all know that. Whenever we have given heat energy to the solid to convert into liquid, we want to make the solid attraction force should be reduced for the case of solid, because for liquid the molecules are not closely packed. Okay, so to reduce this intermolecular force of attraction, I need to work, I need to give some energy, and that energy is latent heat. So latent heat is such kind of heat energy which changes the intermolecular spacing, which changes the intermolecular spacing, or we can say which change the intermolecular attraction. So for case of solid, the intermolecular attraction is more, but liquid it is less. So how this bond should be broken? The strong intermolecular bond is there due to the strong intermolecular force of attraction. How you have to break it? So to break, you need to give extra energy in a form of heat energy, and that heat energy definitely it will not increase the temperature, rather they will change the intermolecular spacing, or they will change the intermolecular attraction. Same thing it is happened when you have taken heat energy, when you have taken heat energy from the molecules, then the temperature should going down. But at a certain time, when you want to take more heat energy, that will make the molecule more closer. The intermolecular space will be less and the intermolecular attraction will be more, and that will never increase the temperature of the body. That heat energy is known as latent heat. So latent heat is mainly deal with the intermolecular forces, and that's why the temperature is not increased by that heat energy. Okay, I think it is clearer for you that what is a latent heat and what is its work. Simple thing, if I have given heat energy to a body, to change the state, more heat energy is needed if the mass is more. So we can write down that latent heat Q is directly proportional to the mass. Here M equals to mass of body. So more the mass, more the latent heat is needed, okay, to change the state. But so here simple example, that if you are having a ice of cube just like this, and assume you are having a ice cube just like this, so both the case, if you want to melt it, so it will take much time because it needs much amount of heat energy. So latent heat is directly proportional to the mass of the body. But here also one thing has come. So what heat energy is needed for ice, if I have taken any another substance, another solid, then the heat energy will be different. Okay, so here we have to take a constant, and that constant we have taken, that is L. So this L, that is a constant, it is having a name. Its name is specific latent heat. What is it? What is physical significance? So this specific latent heat, it is a characteristic property for different substances, and it depends on the intermolecular force of attraction between different body. Okay, and that's why if I am talking about ice, whatever the value of L, if I am taking another solid like wax, lead, iron, copper, then the value of L should be changed. So for different substances, the specific latent heat, it will be different. So if I want to find specific latent heat here, so L equals to Q by M. L equals to Q by M, and this Q is the latent heat energy and M is the mass. So from this you can write the SI unit, it should be joule per kg, and if I am talking about the CGS unit, it should be calorie per gram. Okay, if I want to define it, if I want to define L, how we can able to define it? So to define it, we have to assume that if M equals to 1, then L equals to Q. If M equals to 1, then L equals to Q, and from here we can able to define latent heat. How? We can say that latent heat is the amount of heat energy to change the state of a unit mass substance at constant temperature is equals to its specific latent heat. Again I am telling, the thing is that to change the state of a unit mass of substance, how much heat energy is absorbed or liberated by a body, that is its specific latent heat. Okay, so this is the value of L, and that should be constant. The specific latent heat of a particular substance, it should be constant. Now, as we have learned about L, learn about its unit, then we have to find the relation. So if I find the relation between them, that 1 calorie per gram, that is equals to how much joule per gram. So it is 1 calorie equals to 4.2 joule per gram. So you can say that, sir, it is a mixture of two unit system. Is it possible? Yes. For calorimetry we can take it, but we cannot tell that it is a SI system or CGS system. We can use that system for our general purpose, but we cannot give a name of a special system because it is a combination. But if I want to convert it with joule per kg, so it is also very easy. 4.2 joule, gram means 1 by 1000 kg, so it is 4.2 into 10 to the power 3 joule per kg. So these are the relation between the units of specific latent heat. Now we will show you some example, then it will be easier for you to understand what is specific latent heat. If I am talking about ice, okay, so if I am talking about ice, then the specific latent heat of melting, specific latent heat of melting for ice, if I am talking about it, its value will be 336,000 joule per kg. So this much amount of heat energy, this is the value of L for ice to melt to water. So what I am telling, I also just confused by telling, because now it is almost 12 o'clock at night, and in outside it is a heavy storm has been started. I am just very much eager to do this video because after some days, you know, that maybe the electricity connection will be not there, maybe the net connection is not there, so that's why today I am doing. So what I am telling, that something is gone out of my mind also. So again I am telling the same thing. What is L? Now L, it is the specific latent heat of melting for ice, that is 336,000 joule per kg. That means to convert 1 kg of ice at 0 degree centigrade to 1 kg of water at 0 degree centigrade, to convert it, how much heat energy is needed? Now the heat energy is needed, it is 336,000 joule per kg. So by that statement we can understand this. If I have taken to another unit system, that in CGS it will come 80 calorie per gram. That means to convert 1 gram of water, 1 gram of ice, 1 gram of ice at 0 degree centigrade to 1 gram of water at 0 degree centigrade, to convert it, the heat energy is needed, it is 80 calorie. Okay, similarly, if I want to just take it in opposite direction, that means to convert 1 kg of water to at 0 degree centigrade to 1 kg of ice at 0 degree centigrade, then this much amount of heat, okay, definitely it shouldn't be joule per kg, 1 kg we have mentioned. So definitely this much amount of heat should be liberated or taken out, or 1 gram of water at 0 degree centigrade, when it converts into ice, okay, discussing about some examples, and here we have to see the example of specific latent heat of fusion of ice. What is it? And just now we have seen that latent heat Q equals to m into L, and L equals to Q by M, and it is also told that if m equals to 1, then L equals to Q. Just now we have discussed. So here, from here we can say that when 0 degree centigrade of ice is converted into 0 degree centigrade of water for unit mass, because m we have taken 1, and that time the extra heat that is needed, that should be the specific latent heat of fusion. Okay, so when unit mass of 0 degree centigrade of ice it converted into unit mass of 0 degree centigrade of water, how much heat energy is needed, that is known as specific latent heat of fusion. Or in another sense, when 0 degree centigrade of water converts into 0 degree centigrade of ice by liberating heat energy. 0 degree centigrade of water is converting to 0 degree centigrade of ice by liberating some heat energy for unit mass. How much heat should be liberated by water, that also known as specific latent heat of fusion of ice. Okay, so what is the value of it? The value is 336,000 joule per kg. This much amount of heat per kg is needed. That means whenever you have to convert 1 kg of ice at 0 degree centigrade to 1 kg of water at 0 degree centigrade, then extra 336,000 joule heat energy you have to supply, you have to give, then it will happen. Or in another sense, instead of taking the SI unit of or SI value of this latent heat of specific latent heat of fusion of ice, if I am taking the CGS one, so the CGS value is 80 calorie per gram. That means to convert 1 gram of 0 degree centigrade ice to 1 gram of 0 degree centigrade of water, we need 80 calorie of extra heat energy to ice. Okay, 80 calorie of extra heat energy we have to supply, then this change will occur. Otherwise, in another way also you can represent it, just like if you convert 1 gram of water at 0 degree centigrade to 1 gram of ice at 0 degree centigrade, then you have to take 80 calorie of heat. You have to take, you have to liberate it, extra 80 calorie of heat. In another sense also, 1 kg of water at 0 degree centigrade to 1 kg of ice 0 degree centigrade, that time how much heat you have to extra? You have to extra 336,000 joule. This much amount of heat you have to extra. Okay, so here sometime the question has asked that which one is more cooler, 0 degree centigrade ice or 0 degree centigrade water? What will be the answer? The 0 degree centigrade ice, it is most coolest because it liberated extra 80 calorie of heat. And when I am talking about 0 degree centigrade of water, it will absorb 80 calorie of heat. So extra 80 calorie of heat per gram or 3,36,000 joule of heat per kg extra heat energy is there for water at 0 degree centigrade. But for ice, this heat energy has been extracted from it. So ice of 0 degree centigrade, it is more cooler than the water. Okay, apart from this also, we have taken another unit, that is, it is a combo of SI and CGS unit that is used in our general purpose, that is 336 joule per gram. Actually, we have seen that 336,000 joule per kg. If I convert kg to gram, here you see 336,000 joule per kg. So if I convert kg to gram, so it will come 336,000 joule per 1000 gram. So it is 336 joule per gram. So it is a combo of CGS and SI unit. But we can say when we want to convert 1 gram of water at 0 degree centigrade to 1 gram of ice at 0 degree centigrade, then we have to extract extra 336 joule of heat. That means 80 calorie and 336. These are same. Okay. Instead of using calorie, we are using joule. In another way also you can say that 1 gram of ice at 0 degree centigrade, it will take extra 336 amount joule of heat to convert to 1 gram of water at 0 degree centigrade. So this is the example of specific latent heat of fusion, and thus value you have to remember. If you have not remembered also, it will given in numericals, but better you have to remember these three values. Mainly these two values are there: 3,36,000 joule per kg, that is the specific latent heat of fusion of ice, or in another way 80 calorie per gram. Okay, so these two are CGS and SI unit of specific latent heat of fusion of ice. Now, one another example we have to see, that is specific latent heat of, instead of fusion, we have to write vaporization. So it's very easy. When water at 100 degrees centigrade converts into steam of 100 degrees centigrade, for unit mass, how much extra heat energy is needed, that much extra heat energy is known as specific latent heat of vaporization of, I'm sorry, it's not ice, it's water. Okay, that means when 100 degree centigrade of water, 100 degree centigrade of water of unit mass converts into 100 degree centigrade of steam of unit mass, how much extra heat energy is needed, that is known as specific latent heat of vaporization of water. Or in another way you can say, for 100 degree centigrade of steam of unit mass to convert 100 degree centigrade of water of unit mass, how much extra heat energy you have to taken out, or you have to liberate it from water, that is also known as specific latent heat of vaporization of water. Okay. Now what should be its value? If I am going by the SI unit, its value is 2260 into 10 to the power 3 joule per kg. By see the value, you can understand that the heat is not a less amount of heat. It's a huge amount of heat. If you feel that for converting 1 kg of water at 100 degree centigrade to 1 kg of steam at 100 degree centigrade, you have to supply 2260 into 10 to the power 3 joule of heat. Okay, or in another way, when 1 kg of steam at 100 degree centigrade just converts into 1 kg of water at 100 degree centigrade, then you have to taken out, you have to liberate it 2260 into 10 to the power 3 joule of heat. Okay, if I'm going for its CGS unit, what will be the CGS unit of it? So CGS unit is 540 calorie per gram. By that we can understand for 1 gram of water at 100 degree centigrade, to convert 1 gram of ice, 1 gram of steam at 100 degree centigrade, that extra heat energy you have to supply, that is 540 calorie. Or in another way, 1 gram of steam at 100 degree centigrade to 1 gram of water at 100 degree centigrade, you have to taken out 540 calorie of heat energy. So 540 calorie per gram, or 2260 into 10 to the power 3 joule per kg. This is the specific latent heat of vaporization of water. Okay, so that things you have to remember. Here also we can convert it into CGS and SI, that 2260 into 10 to the power 3 joule per kg, or 2260 into 10 to the power 3 joule per kg means 1000. So this one will be cancelled out. So it is 2260 joule per gram. So another way, 1 joule of water 100 degrees and 1 gram of water at 100 degrees centigrade to 1 gram of water at 100 steam at 100 degrees centigrade, you have to supply 2260 joule heat energy. Or another way, you have to extract 2260 joule of heat energy from 1 gram of steam to convert it to 1 gram of water at 100 degrees centigrade. So this value you have to remember. Okay. Now I have to explain you more about latent heat in an idea of kinetic theory of molecules. Okay, kinetic theory of molecules. I think it will be easier for you. And you, if you have not written this thing, just pause the video and write it down. Okay, then it will be clear for you that what we are going to discuss. So next we are going for explanation of latent heat with the help of kinetic theory. Now I am just giving a little idea of kinetic theory or kinetic model. See, we are discussing about latent heat, and there we have learned about the latent heat of fusion of ice as well as the latent heat of boiling of water. Now the problem is that which is coming to your mind, that what is the need of this latent heat? Whenever we have given that latent heat to a body, the temperature of that body is not changed. So the heat is absorbed by the body, but the temperature of the body is not changed. Then where does the heat go? That is a big question coming to our mind. And now we are just trying to explain it or to solve that problem on the basis of kinetic model. Okay, so our next target is to learn, that is explanation of latent heat of melting and boiling on the basis of kinetic model. Now you see this kinetic model, this term is totally new to you. What is kinetic model? So by the term kinetic, one term has come, that is motion. So we all know due to the motion of a body, what energy is possessed, that is known as kinetic energy. So what is kinetic model? Kinetic model is a part of physics where, as well as the part of chemistry also, where we mainly deal with the motion of the molecules of a substance. So it is very clear that if the motion of the molecules are more, then the kinetic energy of the molecule is more. And if the motion is less, then the kinetic energy will be less. And that theory is very much applicable mainly for the gases, because you know the molecules of gas can able to move very faster. But we can use that model in case of solid and liquid also. Okay, now coming to the point, as we are talking about the molecules of the substance, then let's see whatever the energies are there in the molecule. So definitely in the molecules also there are kinetic energy and potential energy. Kinetic energy, we all know due to the motion of the molecules, what energy is possessed, that is the kinetic energy, that is the motion of molecules. And another energy, that is the potential energy, that is coming due to the intermolecular force. Intermolecular force. So due to the intermolecular force between the molecules, that energy is possessed, that is called potential energy. Okay, in the case of gas, I'm talking about gas because this kinetic theory you will learn clearly in class 11, and there you have to know that in gases, you see most of the molecules are moving here and there, and there the interatomic attraction for the gases, it is negligible. So we can say for gases potential energy is negligible, kinetic energy is maximum. Okay, now we are coming to that kinetic energy because it is on the help of kinetic model. This kinetic energy, it can be changed. We can change the motion. How? If I give heat energy, if temperature is increased, temperature. So if the temperature of the molecule is increased, then they will move faster and then they will get more kinetic energy. So we can say that temperature and kinetic energy, they are exactly correlated with each other. More the temperature, more kinetic energy. Okay, and in opposite also, less temperature, less kinetic energy, right? So that is the relation between kinetic energy and temperature. If you give more temperature, then kinetic energy of the molecules will be increased. And now whenever we are talking about the total energy, so total energy, that you all know, that is potential energy plus kinetic energy. Clear? So that is the basis of kinetic model, nothing else. Okay, that is the basis of kinetic model, whatever we have explained. Now we are coming to the latent heat. So first we are talking about the latent heat of melting, then we will go for boiling. So first we are coming about melting. So melting means this is the process at a constant temperature when solid is converted into liquid, that we all know. Okay, solid is converting into liquid. Now I'm coming to the structure of solid. If I am just studying the intermolecular structure of solid, we all know the molecules are very much closely packed in solid, right? So as per kinetic model, we can say that as the molecules are very much closely packed, so they cannot able to move here and there, right? You have read it in class 6 only, you know that very well. So the molecules are so much closely packed, they cannot able to move. So for the case of solid, we can say here kinetic energy is very less. Now you might be asking, sir, if it is closely packed, then why there will be kinetic energy? Because there should be a vibration between them. Now we are coming why this vibration occurs, but we all know that molecules, they can able to vibrate their own place, and vibration, it is also motion, and due to that the kinetic energy they will get. So for solid we can say the kinetic energy is there, but it is less. As we know, there is a very strong intermolecular attraction, so here potential energy is high. So for solid, we can say potential energy is greater than kinetic energy. Now, what you are doing? You have given heat energy. So heat is given to solid. So what will happen if I have given heat energy to a solid? Definitely the temperature will increase. Okay, so as we have given heat energy, the temperature will be increased. So more temperature, more vibration, right? If you have given more temperature, they will vibrate more, so kinetic energy will be more. Simple thing. If you have given more heat energy, then temperature will increase. More temperature, more vibration, more kinetic energy. So as you have given heat energy to the solid, step by step the kinetic energy is increased, but the potential energy, that will remain same, because potential energy is not related with the temperature. So if the kinetic energy increases, here also potential energy doesn't change, but after increasing it will reach to a certain temperature which is known as melting point. So after increasing the temperature, it will reach to a certain point that is known as the melting point. So melting point, we know, after that the temperature will not increase. Why? What is the reason? The reason is that when the molecule starts vibrating, there will be a limit of vibration. So after vibration, whenever they have gone to the melting point, they have reached to the maximum vibratory level. After that, the vibration is not possible because there is a strong intermolecular attraction. So what we have to do? We have to break. Why? Because I want to convert it into liquid, and we know for the case of liquid, the molecules can able to move freely inside a boundary. Okay, so it is clear that you have to decrease the intermolecular force. So to decrease the intermolecular force and to make more intermolecular separation, some work, some energy is used. That energy is your latent heat. So we can say latent heat is used to reduce the intermolecular attraction and increase intermolecular separation. So that is the work of latent heat. So latent heat is mainly used to increase the intermolecular separation. So as the intermolecular separation is increased, what will happen, you know? So that you have to remember that potential energy is increased. Potential energy is increased. So initially, whenever the temperature goes high, that time potential energy remain fixed. But as the state changes occur, state change means The extra heat energy we have taken as a form of latent heat. What is the work of latent heat? The work of latent is to break the bond and to make the separation more. If you do it, that time the potential energy is increased. So we can say latent heat is used to increase the potential energy at the time of melting. Okay, so that is the work of latent heat. That's why the temperature is not changed, because here the temperature is not increased by giving heat. So that given heat is used to increase the separation, to decrease the intermolecular force. But if I am coming to the opposite way, so that I am talking about melting. Okay, so here as well as if I am coming for freezing, that is the opposite process. So where we have to taking out some heat energy, we have to liberated some heat energy. What will happen then? So then also the opposite thing is happen. If you are decreasing the heat energy here, step by step their motion will be decreased, so kinetic energy will be decreased. But after a certain time, whenever it is reaching to the freezing point, after reaching to the freezing point, then some extra heat energy you have to take, so that the intermolecular force will be strong and the potential energy should be decreased. So here the heat energy should be extracted, and that heat energy is the latent heat, okay, or liberated. And that time that heat energy whatever you have to taken from a liquid, that decreases the potential energy. So that is the explanation of latent heat on the basis of kinetic model. If I'm coming for boiling, I think it is clear enough. If I'm coming for boiling, so boiling is a process, you know, when liquid is converted into gas. So it's a very common process. So when we are discussing about boiling, that case also liquid to gas. Okay, here also we know the liquids can move inside a liquid, molecules can move inside a boundary, so it will have a kinetic energy, but they are having a little intermolecular attraction, so they will have a potential energy also. Okay, as you have given heat energy, okay, heat is given, then temperature is increased, simple thing. And as the temperature is increased, then what will happen? Kinetic energy is increased. Up to how much point? Up to the boiling point. Okay, and at boiling point, whenever it will reach, then the kinetic energy will not increase apart from it. It is the maximum. So for that case, you need to break it. You need to break the separation, because you know for gas there is no boundary. They can move any direction. So this intermolecular attraction will be broken. So how you have to break? You have to give some extra heat energy, that is called latent heat of boiling. And as you have given that extra heat energy, then what will happen? The separation will be more, simple thing. The intermolecular separation will be more, and the potential energy is increased as separation between molecules is more, simple thing. So that's why that heat energy is used to break the bond, to break the intermolecular attraction. So that's why the temperature is not increased. So this is the explanation. And the opposite thing, if I'm talking about condensation, the exactly opposite thing is occurred. Okay, I think it is clear. Now as this thing is clear, now I'm just going that from here, what is the important things you have to remember. So to remember it, I'm telling you one more thing, that here we have to do some numerical. So for numerical I'll make another video, but what equation we have to use, that help I will just give you. So assume the basic equation we have to use, that is principle of calorimetry. So here we have to learn principle of calorimetry and latent heat. So it is clear that latent heat, it is used to change the state. So that case only you have to remember the latent heat where the state changes occurred. So assume I have given you an example. Assume m mass of ice at 0 degree centigrade is kept in water of mass m1 and temperature T1. Okay. After some time, final temperature of the mixture is T. Okay. So simple thing, assume there is a container, here you have kept water. What is the temperature of water? That is T1. Okay. Now you have to put some ice, okay, of mass m. So as you have put ice over here, so its temperature is 0 degree centigrade, I have already told. Then what will happen? The mixture, because that ice will melt. Sometimes we have done that in Coke or in some cold drinks, we put ice cube to make it cooler. Okay, so here also the ice, it will melt, and after melting the mixture temperature is going to T. Okay, now what we can able to do here, see, so here we can write as per principle of mixture or calorimetry, heat absorbed by cold body is equals to heat lost by hot body. Now what is the hot body and what is the cold body here? Simply the water, it is the hot body, and the ice you have given, it is the cold body. And now one thing is happened here, the state of the cold body is changed. So here we can able to mention also, after some time the final temperature of the mixture is T when the whole ice melts. So whole ice melts here, so state changes occurred. Now we have to find heat absorbed by the cold body first. So heat absorbed by ice. Now find how the state has been changed. So initially the temperature of ice is 0 degree centigrade. So 0 degree centigrade of ice, it will first change its state. So 0 degree centigrade ice, it will gone to 0 degree centigrade water. See here temperature will not change, only the state is changed. And then 0 degree centigrade water is converted into T degree centigrade of water. Why? Because the final temperature of the mixture is T. So this is the step what is followed by ice. First 0 degree centigrade ice to 0 degree centigrade water, and 0 degree centigrade water to T degree centigrade water. This flow chart you have to make whenever you have to make any sort of numerical. Okay. Now 0 degree centigrade ice to 0 degree centigrade of water, m mass of ice. So it is clear that here the heat energy it is needed, that is the latent heat. So latent heat equals to how much? Mass into specific latent heat. Let the specific latent heat is L. So m into L plus 0 degree centigrade water to T degree centigrade water. Now here you see in the second phase the temperature is changed. In the second phase the temperature is changed. So from 0 to T. So m specific capacity of heat, okay, C into change of temperature that we have learned in the previous part, that is T minus 0. Okay, so we can write it is m into L plus mc into T. Clear? That much of heat is absorbed by ice. Next, heat lost by water. How much heat is lost by water? See, initial temperature of water is T1 degree centigrade. So T1 degree centigrade water to T degree centigrade of water. Here you see no phase changes occur. Only the temperature is changed. T1 degree centigrade to T degree, and definitely we know that T1 should be greater than T because the temperature should be decreased of the mixture. Okay, so here we can write that heat energy will be, here if you mention the heat is Q1, here heat is Q2, that is M1, that is the mass of the water, okay, into C, because here also it is C, here also it is C, because the specific heat capacity of water should be same, into T1 minus T. T1 minus T. Okay, change of temperature. So heat absorbed by ice and heat lost by water, it is clear to us, and we know this Q1 and Q2 should be same, so we can write as Q1 equals to Q2, so m into L plus m into C into T, that be equal to m1 into C into T1 minus T. This type of, here I have not given any digit, I have just used m1, m2, okay, but this type of numerical will be asked in exam. Okay, what type of numericals will come? For that we will do a special video only for numericals. Okay, so what we have learned, if we summarize little bit, we have learned that explanation, so I think I can able to remove it. So if you are not able to write down, pause the video here and write it down. So what we have learned here, so first we have learned that is explanation of latent heat on the basis of kinetic model. Okay, so if I am talking about an example also, that for 0 degree centigrade ice, when it converts to 0 degree centigrade of water, then extra 336 joule per gram or 336,000 joule per kg or 80 calorie per gram, this much heat energy is used to change the state. So that amount of heat energy is used per gram to break the bond, to increase the intermolecular separation. Okay, and in the last case we have seen that there is a relation that how the state changes occur, then how we can able to use it in principle of calorimetry. Heat absorbed by ice, heat lost by water, we have to make it equal. And assume if anything is not given to us, assume L is not given or M is not given, rest of the thing is given, so we can able to find it out. Now coming to very interesting thing, that as we have learned that latent heat of ice, latent fusion of ice, that is 336 joule per gram, or 3,36,000 joule per kg, or 80 calorie per gram. This heat, this latent heat of fusion is very high. We can say that latent heat of fusion of ice is very high. So this value, if you see, there is a chart given to your book. If you read it, you will understand that this value, it is very high value. Now we have to learn the last part, that is the natural consequences. Natural consequences of high latent heat of fusion of ice. What is the utility of this much higher latent heat? Number one consequence is a very interesting one, that the ice of mountains cannot melt together. So we know in mountains whose height is very high, so in that mountains all time there is ice at the top. So whenever at morning when sun rises, so it may occur that all the ices will melt suddenly, and as it melts suddenly, so suddenly the level of the water in sea, it will increase, but it will not occur. Why? The reason is that as the heat energy is so high, so to reach that much amount of heat energy so that it will melt all the ice together, it is not possible. Okay, so due to that huge heat energy, the ice of the mountains, they will melt very slowly. Okay, so at the morning time and at night, again they will just solidify and they will freeze. So that's why the balance, that the level of the water, the balance of the ice, it will be just maintained. If the heat energy is less, then suddenly it will melt and suddenly there will be flood. First consequences. Second consequence, if I have gone, that the lakes and ponds in pole areas don't freeze together. Okay, so if I'm talking about the lakes, okay, so in lakes there is water. In pole areas also there are many lakes are there, many seas are there. So if I'm talking about their temperature is very less, so they may be just freeze together. But it is also not possible, because due to freezing also you have to liberate, you have to exert, you have to release this much amount of heat energy, so which is very high. Okay, so that's why it is not freeze together. And one of the very interesting thing you have learned in class 9, that in pole areas the surface of the pond, that is just going, and there will be a layer of the ice has come, but below their temperature is 4 degrees centigrade. That is anomalous expansion of water, it is occurred, and that's why the creatures, okay, the water creatures in that areas, they can able to survive. Okay, here also a very beauty of that nature you see. So that layer of the ice, when it comes, this layer of the ice, it work as an insulator. Okay, so if the water beneath the layer of the ice, it is 0 degrees centigrade, if it release the latent heat and if it wants to convert into ice, so to release the heat energy, it have to cross this insulating barrier. So that is also very hard. So that's why it will not just freeze together. So this is the way, due to this huge amount of heat energy, they can able to release. Okay, that is not possible. Number 3, ice cube is used to make the drinks cold, rather ice water. So we prefer ice cube to make our drink cold rather than ice water. Ice water means the water is also at 0 degree centigrade, but the phase is not changed. Why? Because in ice cube, you know that here extra this much heat energy is being taken out, so it is more cool. Sometimes the question has asked, which is more cooler, ice, 1 gram of ice or 1 gram of ice water, or 0 degree centigrade of ice or 0 degree centigrade of water? Which one is more cooler? Definitely it is ice, because for ice you have to take in, for each gram or for each kilogram you have taken this much amount of heat energy, so this is more cooler. That's why this ice cube, it is more efficient to make a drink cold rather than ice water. Okay, so number 4, coming to another natural consequences, hailstorm. So it is a new term to you. So during hailstorm or after hailstorm, the surrounding temperature decreases. What is hailstorm? Hailstorm is it's a storm in cold areas when the ice suddenly melts due to a storm. Suddenly, hailstorm means suddenly ice melts. Okay, so when the ice melts, try to understand, when the ice melts, it have to take this latent heat to change its state. Okay, if a ice want to melt, so it want to extract heat energy from the surroundings to make its state change. So this ice, from where it will extract heat? It will extract heat from the surroundings. Okay, assume one mountain is there which is full of ice. It just want to melt due to some natural phenomena. So when it will melt, it will extract heat energy, because to change the state for melting, it needs extra this much amount of heat energy per kg. So from where the heat will be taken? It will be taken from surroundings. So as the heat is taken from surroundings, automatically the temperature of the surroundings will going down. So due to hailstorm, mainly it is also in pole areas, the surrounding temperature goes down suddenly. Okay, so these are the natural phenomena. All the case we are talking about melting. So for boiling, if I'm going to the last part, that is boiling, so one thing I'm just mentioned here. So if I'm asking you which one is more severe, which one is more severe, 100 degree centigrade of water or 100 degree centigrade steam? Which one is more severe? What do you think? Think. If I'm talking about water, so water to steam, water to steam. So there is a phase change occur. So to make the phase change, you have to give extra heat energy. How much? Either 2260 joule per gram or 2260 into 10 to the power 3 joule per kg, or 540 joule per 540 calorie per gram. So this much amount of extra heat energy you have to give per gram to the water to convert into steam. So this extra heat energy is there in steam. And for water, if I'm talking about 100 degree centigrade water, this extra heat energy is not there. But if I'm talking about 100 degree centigrade of steam, this much extra heat energy is there per gram, or this much extra heat energy is there per kg. That's why 100 degree centigrade steam is more severe. It can make more severe burn rather than 100 degree centigrade of water, because for steam this much amount of extra heat is there as a form of latent heat. So that is the whole story of state change and latent heat. Okay, so theory portion of calorimetry is completed. Now in the next video we'll discuss about the numericals. So before that, read that portion. Any doubt, ask me. Thank you.